When Albert Einstein put forward the field equation for the general theory of relativity, one of the things he did was work out the solution for the equation for the cosmos as a whole. When using the original form of the equation, he found that his model universe wanted to expand, something he thought unlikely. You see, in 1916, when Einstein first published his work, there was no evidence of an expanding universe, or, really, that there was a universe outside of our own Milky Way at all. Instead, astronomers and the fledgling group of astrophysicists that had begun to form around men such as Hale, Pickering, Huggins, and Vogel were still grappling with the size of our home galaxy and our place in it. The discoveries of Shapley were still 4 years in the future, and those of Hubble and Humason lied even further down the road. And so it was that Einstein decided they needed to tinker with the equation just a bit. Since there was no evidence of an expanding universe, he added a single, constant term that could be adjusted by the mathematician to balance the model's tendency to want to expand. If one selected the right value for this cosmological constant, as Einstein called it, something he labeled with the Greek symbol lambda, the term would create a stable and steady universe, at least globally, that neither expanded nor contracted. However, as the community of theoretical physicists who were interested in thinking about cosmology became familiar with Einstein's equation, they began to suggest other possibilities as exercises of physical imagination. They worked out what it might happen if different values of lambda were chosen. First among these was Alexander Friedmann, who solved the cosmological application of Einstein's field equations for a whole class of values, coming up with universes that expanded forever, some that expanded and collapsed in an oscillating fashion, and, if the value of lambda were just right, slowly came to a stop at the very end reaches of time. For his part, Willem de Sitter showed that one could construct a universe with very little mass, wherein the rate of expansion increased over time with the tiny froth of matter speeding away from itself at an ever-growing rate. Of course, Father Georges Lemaitre, knowing of the observations being made in the United States by men like Vesto Slipher and Edwin Hubble, independently derived some of Friedmann's expanding universe solutions in a way that very closely matched what Hubble would soon publish. This work, combined with Hubble and Humason's papers detailing their observations of galactic velocities, established the reality of an expanding universe for nearly all cosmologists. In light of this, Einstein was asked about the necessity of the cosmological constant. Recognizing in hindsight that he had actually predicted the results and yet had not had enough faith in his work, he is said to have called adding the cosmological constant, quote, his greatest blunder, an unnecessary adjustment to a simpler and more elegant equation. Einstein's colleagues, however, were less harsh in their assessment of his decision. While Einstein de Sitter models of the universe that would be published in the 1930s would not include the term, Lemaitre's models always did. His reasoning was that the equation with the constant was a more general expression that could be more closely tuned to the data, and while, over the years, there were always models that included a cosmological constant, these were often pushed to the periphery of mainstream thinking, if ideas regarding the expansion of the universe could ever be said to actually be mainstream. It wasn't until Alan Guth's work on the inflationary universe as a way to explain the observations of the universe's overall flatness that the term began to be reconsidered again. And while it would not be the case that this would be the solution, its relevance was once again brought into the scholarly conversation. This would come to the head when, in 1998, two research teams observing some of the most exotic of astronomical phenomenon announced results that shook the cosmological community to its core. The rate of expansion of the universe was, in fact, accelerating. Once again, the cosmological constant, Einstein's supposed biggest blunder, was relevant, and the implications were staggering. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 49, The Present Puzzle. To begin this episode, we have to start in a seemingly unrelated place, and that is with the death of stars. Like many things in our universe, stars undergo a life cycle from birth, through a long period of maturity, and then finally, through a process of dying. What drives and governs this process, at its heart, is, as my graduate advisor used to say, gravity, that pathological beast. When a star begins to form from a cloud of interstellar gas and dust, what happens is that the mutual attraction of all of those molecules and tiny grains begins to pull a clump of material towards something like a common center. In such a case, the mass is great enough and the temperature is low enough to allow the gravitational attraction between all of those particles to overcome the tendency of those particles' random motion to push the whole thing apart. Once this collapse begins, the material begins a long, slow infall according to the processes first laid out by Kelvin and Helmholtz and then later expanded upon by the British physicist Sir James Jeans. While the details of this process are somewhat beyond the scope of our story here, what's important to understand is that once this process of gravitational collapse begins, it is inexorable. Gravity, by its very nature, will always seek to pull that mass that makes up the forming star towards a common center. The only thing that will stop this collapse is some sort of balancing outward pressure. During the protostar formation stage, this pressure is provided by the heating of the gas and dust, energy that is then radiated away through the emission of infrared light, leading to additional collapse. In time, the temperature and pressure in the core of the star reach a point where hydrogen fusion takes place, and it is the energy released from the conversion of mass that provides the outward pressure to balance the gravitational force and stop the infall. This will continue to take place for as long as the star has enough material to fuse and high enough temperatures and pressures to support that fusion. However, such fuel is limited, and so, given enough time, all of the hydrogen in the core of a star will be fused into helium, and so the energy needed to hold the star up will diminish, and the collapse will resume again. This change marks the end of the star's time on the main sequence of the Hertzsprung-Russell, or HR diagram, and begins a transition to the final stages of the star's life. As an aside, the way an astrophysicist represents a star's life cycle is to plot the star's path on that HR diagram, that figure that places a star on a plot of spectral class or temperature on the horizontal axis and absolute magnitude or luminosity on the vertical axis. In a way, an analogous sort of diagram might be a plot of how a human being changes over time by plotting that person's place on a diagram which has the weight on the horizontal axis and the height on the vertical axis. You can think of the person as being on a point on that graph that moves as the person's age changes and hence his height and weight changes. Early in the person's life, they will start with a low weight and a short height, and over time, the dot that represents them will move to higher weights and heights as they grow up. At some point, they will probably reach a stable height that they will have for most of their adult years. And if they manage to balance their caloric intake and output, their weight will remain reasonably stable as well. As they become elderly, however, the effects of age will probably cause them to lose a little height and gain a little weight, and so they will move away from their adult position on the diagram. Now, if you were to plot a whole lot of people all at the same time, you'd find that while there is some variation in their heights and weights at adulthood, These typically correlate with variations in the weight, and so most adults will spend most of their time in a band on that height-weight diagram. It's the same kind of thing that happens with stars on the main sequence of the HR diagram. Now, as the fuel runs out at the center of the star, gravity's inward pull once again becomes dominant and the collapse begins again, and so the star moves away from the main sequence to a different part of the HR diagram. Once this happens, there are 3 or 4 possible outcomes, depending on whether you're looking at the process that leads to whatever end product you have or the end products themselves. Which of these places a star ends up at actually depends only on one thing, and that's its mass. If a star has a mass that's about 40% that of our Sun, or something less than that even, the temperature and pressure of the star will never reach a point where it can fuse helium into heavier elements. In this case, the star collapses down to what is known as a white dwarf, made of helium and unfused hydrogen from the star's outer layers. Here, the inward pull of gravity is balanced by something known as degenerate electron pressure, an idea we'll talk about here down the road just a bit. Now, if the star is between about 40% of the Sun's mass and about 8 times the Sun's mass, so that's big range in there, what you're going to get is something different. And by the way, the upper limit on that is still subject to a good bit of uncertainty. But what happens here is if you're in that range, the temperature and pressure in the core of the star can get high enough to fuse helium into heavier elements like carbon, nitrogen, and oxygen in Hoyle's CNO cycle that we talked about in an earlier episode. This will build a core made of carbon and oxygen under high pressure that will be resistant to being fused, into elements higher up on the periodic table. At this point, the fusion process in the core will stop, and through a series of pulsations, the star will push its outer layers out into space, wherein the ultraviolet light being given off by the now exposed, super hot core will illuminate the ejected material, forming one of the most beautiful astronomical objects that can be seen, something known as a planetary nebula. This central object, still known as a white dwarf, will cool over time, forming what is, in essence, an impure diamond that's about the size of the Earth. It too will be supported at that point by degenerate electron pressure. If the star is larger than about 8 times the mass of the Sun, it will be able to fuse elements up to iron in its core. But in this case, degenerate electron pressure will not be enough to counter gravity, and so the electrons of the atoms will be eventually forced into the atom's nuclei and will be merged with the protons in the nucleus. The release of energy here will cause the star to explode in a cataclysmic event that leaves behind either a neutron star or a black hole, depending on what the mass of the star actually is. In this event, the elements in the periodic table higher than iron are formed, and a really bizarre object is left behind. In each of these cases, what I hope that you will remember is that gravity, the pathological beast, always has to be balanced. In a very real way, the entire life of a star can be seen as nature attempting to use various processes to stop the gravitational collapse of that original cloud of gas and dust. The end point of this process is basically determined by which physical process, if any, is able to finally stop gravity from squeezing matter into a smaller and smaller volume. For what we want to talk about in this episode, the mechanism that stops the collapse that we're interested in is this thing that we've called degenerate electron pressure. And this all has to do with something we talked about way back in Series 2, what's known as the Pauli exclusion principle. Back in the late 1920s, Wolfgang Pauli was working with the equations of quantum mechanics when he determined that for particles that have a property known as half-integer spin, things like electron, which have spin of plus or minus 1/2, he found that they couldn't occupy the same quantum state as another particle that has that same half-integer spin. When he saw this, he understood why all of the electrons in an atom can't all be found in the lowest energy state, something known as the ground state, at the same time, but instead had to fill up an atom's quantum energy levels from the bottom up. So the way this gets applied to a system like the core of a star that's under enormous pressure is that as fusion comes to a stop, there's no energy to provide an outward pressure to hold things up. And so gravity starts to squeeze the matter into a smaller and smaller volume. At some point, even though the temperature is really high, the pressure gets to the point where it begins to force electrons down into the ground states of the atoms, meaning that they can't get any closer to the nucleus of their atom, and neither can anything else, since the electrons in one atom will repel the electrons in another. This electrostatic repulsion will stop the gravitational collapse as long as the inward gravitational pull doesn't exceed the repulsive force of the electrons in their ground states. The man who worked all of this out was an Indian astrophysicist by the name of S. Chandrasekhar, who was able to show that as long as the mass of the white dwarf didn't exceed 1.44 times the mass of our sun, something known as solar masses, the degenerate electron pressure could support the mass that was being pulled inward by gravity. One of the really bizarre and cool things about this is that as the higher the mass of the white dwarf is, the harder gravity pulls the atoms together, and so the smaller the white dwarf becomes. In other words, the more stuff the white dwarf is made of, the smaller it is. The density of the matter is such that all of the mass occupies a space that's about the size of the Earth, and so, squeezed together so closely, about 5 or so million tons of the material fits inside a bottle cap for a typical soda one might buy from a vending machine. Okay, this is all well and good, but how does it relate to our story? Why did we start with the life cycles and, more importantly, the deaths of stars to come back and talk about these cosmological topics? Well, it really all comes back to the idea of using standard candles to determine the distance to things. In a previous episode, we talked about some of the different ways to do that, but when you're trying to look a long ways out, there are really two things that are super important. First, the candle has to be really bright. And the second is that the candle has to be the same every single time so that it can be used as a standard. So when you look at Cepheid variables and bright galaxies, you get the second of those things pretty well, but you soon reach a limit on the first. In other words, they're just not bright enough to see far enough out to really get at what you want to look at if you're trying to do cosmological kinds of things. They're only so bright, and so, after a while, you can't detect them well enough to get really good data. What you'd really like to find is something that's even brighter than those things. Fortunately, that exists. A moment ago, we talked very briefly about a star that blows itself up, what we call a supernova. Now, when this happens, the amount of energy released actually exceeds, for a very short period of time, the total amount of energy being given off by an entire galaxy by a couple of orders of magnitude. To use our analogy from our older episode where we first talked about these things, think of a supernova being like a flashbulb going off in a field full of people holding candles. The candles certainly burn steady and long, but they aren't going to match the brightness of a flashbulb for that short period of time when the flashbulb goes off. Okay, great, so let's use supernovas. Well, we could, except that there's a problem. For the type of supernova that you get from a high-mass star exploding, designated as a Type 2 supernova, each event is different. This is because different stars have different masses, and the physics of when each supernova takes place in the death process of the star isn't as well as understood as we'd like because the composition of each of the stars is different. So, while we get a bright thing for our standard candle, we don't really get the standard part very well, which is kind of a bummer. What would be better is if we got a supernova occurring from a class of stars that all had the same structure and composition. In theory, this would create a bright object that went through a light curve that was very well calibrated and thus very standard. And this is where the white dwarfs come in. The higher mass white dwarfs are basically all identical in their composition and structure, being made basically the same percentages of carbon and oxygen, especially if they're near the Chandrasekhar limit that we mentioned, that 1.44 solar masses. Now, if there were a process that could add a little bit of mass to that white dwarf, as the mass got added, a little bit over time, a little bit more over time, Once the mass exceeded the Chandrasekhar limit, the mass of the white dwarf that is, the electrons would be pulled into the nuclei and the white dwarf would explode in a supernova. And this time, that would happen with a very standard light curve. This is what we call a type 1a supernova. So, how can that happen? Well, there are two ways, and both have to do with having stellar friends. As we've mentioned, stars are almost always formed in clusters, as they're born from these giant molecular clouds where groups or small parts of the clouds collapse to form a lot of stars at about the same time. You can see one of these star-forming regions if you take a look at the Orion Nebula through a pair of binoculars or a small telescope. Now, when these stars form, about 70% of them end up forming close enough to one or more other stars that they become gravitationally bound to each other, and they form double or triple stars or even groups of stars with more than that. Now, since the lifetime of a star depends on its mass, the more mass you have, the faster the star burns fuel, and the faster the star dies. So, if two stars that are perhaps locked together gravitationally and thus are orbiting each other aren't exactly the same mass, one will end its life before the other does. Now, let's take an example. Let's say our two stars start out with having, say, 3 and 2.5 solar masses. In this case, the more massive star will become a white dwarf before its partner does. Now, if the two stars are close enough together, what can happen is that the white dwarf can gravitationally siphon hydrogen off the outer envelope of the other star, especially if the other star is expanded to its red giant phase. When that happens, the white dwarf will add mass. And over time, it'll add enough mass, maybe, that it'll be pushed over the Chandrasekhar limit and explode, thus generating our type 1a supernova. The other way you can have this occur, by the way, is in case you have, let's say, those two stars actually aren't quite that close together, and so one becomes a white dwarf and then eventually the other becomes a white dwarf, and you have now two white dwarf stars that are orbiting each other. What we know will happen as these two white dwarf stars orbit each other is that they'll radiate energy away as gravitational waves. This loss of energy will cause the two white dwarfs to spiral in towards each other and eventually combine, pushing them over the Chandrasekhar limit and causing that type 1a supernova. Now, this may all seem like a pretty unlikely thing to take place. You got to have a lot of stuff that kind of lines up. And in a way, it kind of is. But what you have to remember is that the Milky Way galaxy alone has something like 1 trillion stars in it. And there are more than 100 billion galaxies that we can see. So what that gives you is 10 to the 23 total stars when we look out into the cosmos. If that's the case, well, something can be pretty unlikely, and with that many chances, it'll still happen relatively often. So the idea in using this standard candle in our analogy is to stand in the field and wait for the flash bulbs to go off. And when they do, you hope that you're looking in the right direction to see them, and then measure the rise and fall in the amount of light the flashbulb puts off. If all the flashbulbs are made the same, then the curves should all be the same. And you can, once you get some calibration measurements from flashbulbs that are nearby, say type 1 supernova events in the Andromeda or Triangulum galaxies, you can get a distance to the flashbulbs that are farther away. Now, since they're so bright, they allow you to see not only across the field that you're looking in or into another field nearby, but they'll let you look out into fields that are all the way across town or even into towns farther away. In the mid-1990s, two teams of astronomers decided to use these standard candles to try and answer some questions. What they found out was really not what anyone expected. The basic question the teams were trying to get some insight into is one that we've mentioned briefly in a previous episode: the ultimate fate of the universe. On a personal note, I remember this being the quote-unquote, all in capital letters, big question when I was in high school. All of the popular science magazines, from Discover to National Geographic, ran stories about what was going to happen down the line billions of years into the future. I remember also being intellectually curious about the science, but really kind of unengaged by all of it. It's not that I didn't think it was good work. I just couldn't see why so many people were getting so worked up about something for which there was so little data, and that didn't seem like it really made a whole lot of difference. I found the development of the standard model of particle physics and the search for the various subatomic particles such as quarks and various mesons a lot more intriguing, not to mention anything about dark matter. To be honest, what I was really excited about were the various processes we were beginning to understand in terms of star formation. Nevertheless, there did seem to be a lot of people, journalists at least, who spent a lot of time trying to figure out what was going to happen in the distant future on the grandest scales of the cosmos. And by the way, I guess I have sort of the same attitude about time travel. I know a lot of people are really wound up by the possibility that we might be able to move backwards and forwards in time in a way that we control, but I just can't garner up a whole lot of interest in it at all, I guess. I suppose the reason is that I don't think we've done a really good job of nailing down what time is and how it works very well, and so I find all the speculation on the topic more the realm of either philosophers or science fiction writers. Not that there's anything wrong with that, it's just not something that I get all worked up about in a scientific sense. So anyway, enough digression. Let's get back to what we were talking about. The question here is, what is the ultimate fate of our universe? Is it closed? In other words, will the expansion eventually stop, reverse, and end up in a big crunch? Or instead, is it open, meaning that there's not enough mass to stop the expansion, and so the universe will continue to grow at an ever slower pace while the galaxies recede from each other and stars convert mass into energy until everything that can be fused has been fused, and the universe grows dark and cold. In other words, a big freeze. Or are we balanced between the two? The answer the data seems to suggest, though this is due probably as much to the effects of the universe's inflationary period to actually that being the way the universe is. So the idea was that if we could look out as far as possible into the universe and measure the light coming from things that are further and further away, we might be able to get the answer to that question. And this meant that a really bright and standard candle would be needed, hence the interest in type 1a supernovae. Now, to understand the goal with these observations, you need to remember, and we said it before, the further out you look, the further back in time you're looking. As the light from some distant object travels through space-time, that light will be stretched and reddened as the space-time expands. Light emitted from supernovas nearby won't be stretched very much, while light from further away will be stretched more. The idea was that if you look at a lot of type 1a supernova at a bunch of different distances, you can reconstruct the expansion rate of the universe, not just now, but how it has changed or what it has been back through time. Before we get into the results of these sorts of observations, it's probably useful for us to define some terminology and what it has to do in terms of what it means for causes of expansion or lack thereof. What astrophysicists tend to do is to refer to things that will cause things to expand or contract in terms of pressure. Now, the weird thing, at least in my way of thinking, is that things that cause contraction are said to have or create positive pressure, while things that would cause expansion are said to have negative pressure. In our example from stars that we used earlier, gravity would exert a positive pressure while some other thing, the motions of atoms or emitted radiation from fusion or degenerate electrons, would provide the negative pressure to balance out the gravitational positive pressure. In stars, when the positive and negative pressure balances, that's something known as hydrostatic equilibrium. So when we talk about the expanding universe, we can do the same kind of thing. Again, gravity, which is produced by mass consisting of both luminous and dark matter, stuff we learned about last time, that all will create a positive pressure. While radiation, light in other words, will create negative pressure. In the inflationary period, the energy trapped in the supercooled Higgs field is thought to have created a huge negative pressure that caused exponential expansion of the very early universe until the phase transition that broke the Higgs field took place, and the energy that was stored there was released to form matter and energy. In other words, start the Big Bang. Now, the other thing you have to remember in all of this is that the density of matter in the universe will fall off as a function of the third power of the size of the universe due to the fact that volume is length times width times height, giving 3 powers of length. Radiation, on the other hand, has that same thing. The density drops as the universe expands by the third power, but it also falls due to the fact that as the universe expands, wavelengths of light stretch out, and so that means that radiation falls off as the fourth power. So when the size of the universe doubles, the density of matter is 1/2 of what it was times 1/2 of what it was times 1/2 of what it was, or being 1/8 of what it was, while for the radiation, the density of that radiation is 1/2 times 1/2 times 1/2 times 1/2, or 1/16 of its original value. What this means is that early on, the universe will expand at an increasing rate, and then when the matter density becomes more important, because its density is falling at a much slower rate than the radiation density, that means that the positive pressure of the gravity will act more strongly than the negative pressure of the radiation, and the rate of expansion should start to slow down. The question is, does the rate slow down enough to eventually reverse the universe's expansion or not? And that's what the two teams of astronomers had decided to try and figure out by measuring the distances to these Type 1a supernovae. Now, to emphasize, this was a tremendously ambitious undertaking, because what you have to do is catch a white dwarf in the act of exploding while you're pointing a telescope of some sort at it. That's not a trivial thing to do. One of the teams was known as the Supernova Cosmology Project, while the other was called the High Z Supernova Search Team, where the term High Z sort of relates to the fact that the galaxies that they're trying to study were to have very large Doppler redshifts to their spectra, and Z is the number that sort of is used to characterize that redshift. So High Z galaxies means they have big redshifts and that they're a long ways away from the observer. The goal was to measure supernova so far away that the stars had blown themselves up at a point when the universe was less than half its present age. And they worked to get a series of supernova from a lot of different distances and hence a lot of different times. And then to use all of that to reconstruct the expansion rate of the universe as a function of times, with the hope of answering the fate of the universe question. The results they got really surprised everyone, at least sort of. By early 1998, both teams announced that based on their observations, they couldn't account for their data with a universe that only had matter and radiation that were causing expansion. What seemed to be needed was an additional source of negative pressure. In March of 1988, the High Z team published an additional paper that showed that not only was this source of negative pressure important, in fact, it had to dominate the makeup of the universe. In September of that year, the Supernova team published its results, both confirming the higher Z results and actually showing that the negative pressure was causing the rate of expansion not only to remain constant, but to actually increase after a certain time in the universe. By December of that year, astrophysicist Michael Turner had coined a new term for this source of negative pressure. He called it dark energy. So the question now comes up, what is this dark energy? First, what you need to understand is that the term itself is just a placeholder, an instrument, if you will, to stand in for what might be creating the negative pressure that is causing the universe to expand at an ever-increasing rate. The reason it had been called this was in sort of an analogy to what Alan Guth had done with inflation. The question was, what was causing it? Well, it turns out that there are a whole bunch of possible theoretical candidates. things with weird names like cosmic strings and domain walls and other sorts of bizarre hypothetical entities. The other possibility, though, is that the cosmological constant in Einstein's field equations isn't actually zero. What this would mean is that there would be some form of energy inherent to space itself that would not diminish as the space expanded. Much like what had happened with the inflationary period, this energy would push space apart at an increasing rate. So how do you tell the difference between all of these various hypothetical ideas? Well, it turns out that when you plug each of the possibilities into various types of theory, they each predict a rate of expansion based on a parameter called W. While this parameter can have any value, at least, in terms of the theory, from negative infinity to positive infinity, the interesting thing is that when the math actually gets done, the values always come out in multiples of 1/3. Radiation gives a value of positive 1/3, slow-moving matter has a value of 0, cosmic strings have a value of negative 1/3, and the cosmological constant gives a value of negative 1. So, once you have that, what you do is you look at your measurements and see what value of W you can see within your limits of error by looking at all of this data. And this means using that type 1 supernova data as well as whatever other standard candles you might be able to think of you can use in as far out as they'll allow you to use them. When all this is done, what you get is an observational value of W that's negative 1 plus or minus about 30%. This alone rules out everything that anybody's thought of, at least up to this point, but the cosmological constant solution. And that's a huge result. Now, as we mentioned in the last episode, if this were the only line of evidence, we'd be wise to hold it very loosely, as it were. While it might have been the best explanation for one set of measurements or another, that's really not enough. What happened after the announcements in 1998, though, was that a number of other observations were devised that would test the idea to see if it could hold up. And these observations are things that we've kind of already mentioned, and they included looking at variations in the cosmic microwave background radiation, the way in which galaxy clusters and the length scales at which galaxies clustered, gravitational lensing, and things like that. In each case, what we found is that this dark energy is overwhelmingly responsible for the expansion of the universe. In fact, the most recent measurements made by the WMAP and Planck satellites tells us that the universe is made up of about 68% dark energy, 27% dark matter, and 5% luminous matter. In other words, we only see 5% of what's important in the universe. Thus, with this result, we can now reconstruct the evolution of the universe after the Big Bang. Once the universe got large and cool enough for the radiation to decouple with matter, its density dropped off much faster than that of matter, and soon the positive pressure of matter began to dominate both the negative radiation pressure and the small negative pressure that a cosmological constant would introduce. During this time, the rate of expansion of the universe slowed. This occurred until about 7.8 billion years ago, and at that point, the matter density fell to the point where the positive pressure that it created became smaller than the negative pressure the dark energy associated with the cosmological constant sort of created. At that point, the rate of the expansion of the universe began to increase and has done so ever since. So, what's the fate of the universe? What it would seem like with this data is that we're actually sort of headed towards a big freeze. But that's kind of a hard thing to say. And why is that? Well, that's because we don't actually know what this dark energy associated with the cosmological constant actually is. And there really aren't a whole lot of great ideas that say whether this energy is associated with a field of some sort, or if it's actually even more complicated than that. Hence, we don't know if, as was the case of inflation, there will be a point of transition where something happens with the field that releases the energy to form new particles, or even maybe if that isn't actually what's taking place now in some way, that forms things like axions that make up dark matter. What we do know is that due to this expansion of spacetime itself, more and more galaxies are slipping from our view. This is because as space is created in between the galaxies and us, especially the galaxies that are very far away, through expansion, the light that is traveling across an ever-increasing gulf of distance takes longer and longer to reach us. Thus, if the galaxy is far enough, as the universe is expanding, the light never actually gets to us, and so we lose sight of that galaxy in a process known as reddening. If the expansion continues, sometime in the very distant future, we'll actually reach a state where only those galaxies in our local group that we are gravitationally bound to will be visible. Of course, by then, we'll have merged with the Andromeda Galaxy and eaten both of the large and small Magellanic Clouds. At that point, we'll truly be in the state Harlow Shapley once thought, where only our galaxy is visible to us and there will be nothing else visible throughout the reaches of the cosmos. Of course, by then, the Sun will be a white dwarf itself, and the Earth, should it survive the stages of the Sun's stellar evolution before that, will be a burnt-out and lifeless cinder, and humanity, if it is to have survived, will have moved on to some other world. And so it is here that we come to the end of this long journey that we've been on. I started this series almost 2 years ago, on December 25th, 2015, with an episode I hoped would encourage you to go outside and look up at the sky. Here we are, some 97 episodes later, and my hope is still the same, that you would go outside this evening and spend some time looking up at the darkening sky. Appreciate the heavens and the way they beckon to the human imagination and have done so for millennia. Know that as you look up, you join thousands of generations of our ancestors who have done the same thing. A lot has happened over the last 2 years. I finished a sabbatical year at Berry College and returned to my home institution here at Gordon State. I survived getting run over by a semi-truck, and I'm a long ways down the road of recovery there. I've even returned to riding long distances regularly, something that just amazes me to this day. I know that for many of you there have been numerous changes as well. Some of you have started college, while others have finished. A number of you have gotten married, some have had children, and a few have separated from their partners. Many of you have traveled great distances and seen a great deal of our world, and hopefully noticed the skies while you were there. Some have moved to new homes while others continue to make memories where they have been. 2 years can seem like a long time, but as we've seen, it's less than the fraction of a blink. Over that time, however, we've traversed an even greater duration. We've been from Egypt to China to Mesoamerica to see how those who came before us saw the skies. We've examined the spheres of Aristotle and Eudoxus, and the deferents and epicycles of Ptolemy. We've traveled to Baghdad, Cairo, and Toledo, and followed the ideas preserved and improved on by the Hakim there that were transmitted back into Europe, where they helped reinvigorate the Latin culture. We've considered the work of priests and monks and canons that eventually overturned the old way of seeing things and began the process of moving the earth from the center, something that continues through to this day. We have reimagined space and time not just once, but twice. We counted and surveyed the heavens with ever more powerful telescopes in order to learn that the universe is a dynamic place, filled with things that boggle the mind and defy the imagination. It has been a profound journey. For me, the takeaway from all of this, the one thing above all, is the recognition of the power of the human intellect. In just 10,000 years, or perhaps 500 if you want to date the real start from Copernicus, we have not only discovered our place in the cosmos, but have come to understand some of the most amazing processes that take place within it. We can tell what something is made of and how fast it is moving from just the light that it gives off. We can recognize how mass influences the motion of other mass, and we know the interplay between mass and energy and how that constructs the universe in which we live. It is a truly remarkable story. Yet, throughout these past 2 years, I have to admit to feeling as if I have failed in telling the story as completely as I would have liked. So often, there was more that I wanted to say that didn't make the narrative. Too often, there wasn't enough time to research things as completely as I would have liked, or to follow a thread as far out as I might have wished to. There were many observations and experiments that were glossed over or neglected, many contributors whose voices were not heard. And so, with as much as has been said, some 700,000 words, there is still more to be studied. If your curiosity has been whetted by this series, I would encourage you to dig deeper. Follow that thing that caught your interest and see where it leads. Read the work of those much more knowledgeable than I and set off on new journeys of your own. Let this voyage not be an ending, but rather a beginning. And for those of you who aren't quite ready to be done just yet, never fear. Over the next month or two, I'd like to release a series of episodes that are more biographical in nature. I have finally received some of the sources I've been waiting for, and so I'd like to talk about some of the lesser-known figures that we've only had a chance to touch on. Individuals like Eddington, Slipher, and Lowell. I'd also like to do an extended series on Einstein, something a number of listeners were in favor of. And if you have a subject related to what we've been talking about over the last 2 years, you can let me know either at our Facebook page, you can email me at cldavies@mac.com, or you can shoot me a message on Twitter. I'm at Chad Davies, and let me know what that is. At the end of our second series, I was able to put in a nice discussion on the topic of metallurgy, and if there's something you'd like me to discuss, I'll be happy to see if I can work that in as well. Also, I would like to post a few graphics in support of this episode, namely the stellar life cycle on the HR diagram and the light curve for a Type 1a supernova, and you can find those at our website, thescientificodyssey.typepad.com. I'd also like to thank the folks at That Music Collective who's been kind enough to allow us to use their compositions, the Blue Dot Sessions. They have formed the soundtrack for our journey, and for that, I am deeply grateful. Finally, in terms of the episode release schedule over the next week or two, we're wrapping things up here this week at the college and are heading into finals. As you might imagine, this is going to mean a lot of grading for me, which does have a way of getting in the way of my reading and research. So if there's a bit of a delay in getting the next episode out, I hope you'll forgive me. So, as we close up, let me encourage you once more to head out into the evening and take a look into the night sky. Take along with you those first 4 or 5 episodes of this series and listen along again as you do your observations and see if you can follow the story of that navigator that we talked about who was in training, this time with an appreciation of the long story of finding our place to add some richness to the account. So until next time, full sails on your journey.